We had so far discussed primarily linear operations like multiplication by a constant, subtraction, addition, and then integration, differentiation. All these are linear operations. For example, filters were solving a linear differential equation, oscillators also. So, now we are going to discuss about nonlinear operations. So, in this the most important block is what is called as analog multiplier. Multiplier here means I am multiplying two currents or two voltages. It is not multiplication by a constant, which was the linear operation we discussed as amplifier or attenuator earlier. Here it simply means multiplication by two voltages or currents. Strictly speaking, multiplication operation as defined by an ideal device indicating that it is multiplier. It has two inputs. One input will be having, let us say, Vx as its input, another let us say Vy, output V naught. This is the symbol for the multiplier. So, V naught is going to be equal to a function of normally two inputs now, Vx and Vy, normally for anything, any device put here is going to be a function of Vx and Vy. How will it be? Normally it is going to be equal to a factor which is independent of Vx and Vy, okay, that we call as voltage, which is an offset voltage, is independent of Vx and Vy. This we call as an offset. Same thing is true with amplifiers also. In the case of an amplifier, it is a function of only one input because it is just one input Vx. Okay. So, output is a function of only one input Vx, but then it could be independent of Vx, which is also called offset there. So, V offset then plus. In general, we can have what is called Kx, which is an output only due to Vx. In the case of an amplifier, this is important, right, and it will be also similarly dependent upon Vy. These are all linear terms which might exist in general. These are called, in this case of multiplier, these are called unwanted terms. These are called feed through, X feed through and Y feed through component. This is X feed through component, this is Y feed through component. This should not occur in a multiplier. In an amplifier, these are things which are supposed to be available. Next, we have K naught into Vx into Vy. This is the product term which we want. Then terms which will be dependent upon Vx squared, Vy squared, Vx squared into Vy, Vy squared into Vx, these are all called nonlinear terms in multiplier. Further nonlinearity. Right. Please understand that this itself is a nonlinearity which is being exploited here. These are the linear terms, these are independent of the input. So, in any nonlinear device, okay, you can get all these terms. If it is going to be a good multiplier, you have to select the configuration in such a manner that only this exists. Kx is 0, Ky is 0, offset is 0, and this also should go to 0. That means, the choice of the configuration should be such that these are going to 0 automatically, and that configuration is ideally suited for multiplication. So, we will see what is the configuration that will give that. Then K naught is obviously equal to 1 over some V reference. It is, in order that the output is a voltage, you are having product here. So, this should be 1 over voltage, right. So, it is a dimension of 1 over some V reference, and in a standard multiplier this has been made equal to 10 volts. In a precision multiplier available as IC multiplier, this V reference has been chosen as 10 volts. So, that Vx and Vy, the dynamic range within which this is going to operate, will also be restricted to 10 volts. That means, if Vx is 10 volts, Vy is 10 volts, V naught is going to be 10 volts if you select Vr as 10 volts. So, that means, this multiplier is compatible with another multiplier which is having the same dynamic range, right. So, we can couple these multipliers without any difficulty and have no problem about dynamic range of such things. That is why this has been standardized. So, in an IC multiplier, therefore, Vr is 10 volts. In other types of multipliers which we are going to use for communications, Vr can be any value, okay, depending upon your application. So, this is a precision multiplier, IC multiplier, which is going to be usable over the widest voltage range, and such IC multipliers are available for about 1 megahertz or so operation. Now, let us therefore think of ways and means of designing multipliers, and then see how these multipliers can be used for a variety of applications like modulators, demodulators. These are all communication circuits, mixers, and these are also called modulator, demodulator is also called modem, which is one of the important unit these days for computer communication. Okay. So, we must learn about how such modulations and demodulations occur in any system. Now, this also forms an important unit in what is called phase detector, then phase lock loop. So, the application of these are enormous: phase detector, PLL, phase lock loop. All these things require the use of a multiplier. Therefore, let us understand first how multiplication is done by selecting a proper configuration, then go over to a discussion of applications in all these areas. As far as the multiplier I mentioned about is concerned, the IC multiplier, there are 4 adjustments to be made before using it. First is to make the offset equal to 0 by making Vx equal to 0 and Vy equal to 0. So, you make Vx equal to 0 and Vy equal to 0, then make the offset go to 0. That is called offset adjustment. This is the first adjustment. Then make Vx equal to 10 volts, okay. Make Vy equal to 0 after this adjustment is made. Already offset has gone to 0, okay. So, now you make Vx equal to 10 volts and Vy equal to 0 volts, okay. Then adjust Kx, that is the feed through component of x, okay. It is only because of existence of Kx that Vx will come. So, this goes to 0. Then the third adjustment is obviously Vy is equal to 10 volts and Vx equal to 0 volts, okay, and make now only thing that can come out is Ky or y feed through component, okay. This is going to be adjusted to 0, and finally make Vx equal to 10 volts, okay, Vy equal to 10 volts, and make V naught equal to go to 10 volts. Keep Vx equal to 10 volts and Vy equal to 10 volts and adjust such that V naught goes to 10 volts. That means, then Vr would have become 10 volts. by making this adjustment, so that V naught is maintained at 10 volts, VR would have automatically been adjusted to 10 volts. So, these are the 4 adjustments that have to be made in the case of a precision multiplier before it is ready, and we can say that V naught therefore is going to be equal to Vx Vy by 10. So, once you say that, thereafter you do not have to keep telling that okay, this multiplier is usable for a dynamic range of Vx Vy less than 10 volts, okay, greater than minus 10 volts. All these things are understood. So, if I now put that symbol for the IC multiplier, I do not have to say that input and output are limited to 10 volts, that is taken for granted. Okay. But these 4 adjustments have to be made before this can be concluded. Okay. So, what is really a multiplier? Strictly speaking, we can understand multiplication from our old usage of log anti-log tables. We used to perform multiplication during those old days. The present generation people are not aware of log anti-log multipliers because of the advent of calculators. But in the olden days, log anti-log multipliers were part and parcel of every engineer, okay, for calculation purpose. That means, logarithm amplifier is necessary for multiplication. That is one method of multiplication. So, we will first discuss the good old ways of multiplication by taking log of a voltage and adding it with log of another voltage. So, I just take log of Vx and add it to that log of Vy, okay, and then obviously it is Vx Vy by another voltage 10. So, add this and subtract log of 10, right, and then take anti-log. I should therefore get Vx Vy by 10. This is as simple as that. That means, I take log of Vx and take log of Vy and add them together and subtract log of 10, okay, and then take anti-log, then I get Vx Vy by 10. Now, when I do this design, I can also design a divider. Please remember, I can take log of Vx and log of Vr and subtract log of Vy. Okay. So, then I will get Vx 10 by Vr. Okay. So, simultaneously I can design a multiplier dash divider. Only thing is the input these things will be varying, that is this is Vx, this is 10 and that is Vy, then it becomes Vx 10 by Vy. So, therefore, in this case of log anti-log multiplier, this is called log anti-log multiplier. The basic principle of this is just this. So, in order to understand this, right, in fact, all these things are not log to the base 10, they are natural logs. Okay. So, natural anti-log, right. Okay. But it is always termed as log anti-log. Okay. Now, let us see how therefore log amplifiers are built. So, now we are going to discuss an important design factor called log amplifier. We have to understand how to take the logarithm of a voltage. This is a nonlinear operation. This itself is a nonlinear operation. This is also called an important communication building block. When you take a logarithm of something, you are actually compressing the entire thing, because you consider log of 10 is 1, okay, log of 100 is 2, log of 1000 is 3, right. So, you are compressing the information in a very short range. So, this is called a compounder. Okay. Again, this is an important unit of communication. Right? You want to compress some voltage or current. Okay. Therefore, you can use this particular unit, log amplifier. So, that log amplifier forms part of a unit called multiplier. So, it is better to understand first this basic unit called log amplifier. How to build a log amplifier? This can be very easily built by using a very important component that we had discussed earlier, that is a diode. In the case of a diode that we had discussed long ago, we know that the voltage and current relationship semiconductor diode is logarithmic. That means, the current in this diode, forward current, when it is forward biased, okay, that ID is equal to I naught exponent V diode by Vt minus 1. This is known to you, right? Vt being equal to 25 millivolts at room temperature. This is approximately equal to, if it is remaining in forward, exponent V diode by Vt, because its characteristic only in the forward bias region is going to be exploited for logarithmic operation, right. For therefore, currents which this I naught may be of the order of picoamperes, okay, or so. So, this under normal bias conditions is going to be something like this approximation. So, if this is the case, V diode therefore equals, okay, Vt log I diode by I naught. From this, that means, this is the log operation, this is the log operation of the current, and this is the anti-log operation of that. So, by using this current and voltage interchangeably, we can perform both log and anti-log operation. How do we therefore convert this into voltage operation? So, I know that the current, if it is made to depend upon a voltage, this will be output voltage of the diode, okay, is going to be Vt log voltage by something. Right. So, I have to make this current become depend upon a voltage. That can be easily done by putting this diode in the feedback loop of an op amp. We know that this op amp, if it is now connected in the feedback loop like this, and we take this output voltage V naught, this should always remain forward biased. That means, the current in this direction should keep flowing, because that current alone can keep the diode in the forward bias mode. So, what is the current here? If this is Vi and if Vi is greater than 0, then only the current direction is going to be this. So, this is a log amplifier only for positive voltages. So, here therefore, please remember that Vi is restricted in its polarity, it cannot be changed. So, here it should be always positive. So, if I have a resistance R here, the current in this which will forward bias the diode will be in this direction if Vi is greater than 0. Okay. Then the current in this is Vi by R, which is going to forward bias the diode, and therefore, the voltage across the diode is going to be the output, it will be plus here minus here, therefore, it is minus V diode, which is minus Vt log, okay. What is I diode? Vi by R. So, Vi divided by R. So, this is what is called a log amplifier, strictly speaking, a very simple structure where I have exploited the property of the diode where voltage and current are logarithmically related, and then put the op amp here to convert the voltage into current and made the current pass through the diode in the forward direction and developed then a voltage across the diode, which became the output voltage. Is this understood? Now, the same thing can be done using a transistor also. So, what do we do? The emitter base junction of a transistor is similar to that of a diode, that we know. So, suppose we have a transistor instead of a diode. This is going to be forward biased, and if this current is IE naught, IE is going to be IE naught, IE is going to be IE naught exponent VBE by Vt approximately equal to, when it is forward biased. So, instead of a diode I can use a transistor connected as a diode. Let us see. So, we know that when the base to collector junction of a diode is shorted like this, it acts as a diode. This we have used in the current mirror also, right. Base to junction is shorted, it is being used as a diode which is forward biased in this direction, right. So, this is a transistor connected as a diode. There is no difference between this and a diode as far as the terminal characteristics are concerned. Now, what is the collector to base voltage here? 0, because I have shorted it. Instead, I can remove this and also connect it to ground. Now, what is the voltage here? It is still 0, because this is ground potential and this is virtual ground potential because of the op amp. So, whether it is physically shorted or connected in this manner, okay, the transistor is still acting at VCB equal to 0. With VCB equal to 0, we had that diode connection, but now this is acting as a transistor, please remember, with VCB equal to 0. What does it mean? When I inject a current of Vi by R, in order that this is to remain as virtual ground, this current should become equal to Vi by R. That will happen by base to emitter voltage now from ground to this point getting generated as equal to minus Vt log Vi by R into I naught. So, that means this automatically develops an output voltage because of the negative feedback, okay, such as to pass this current in the collector. So, this is a log amplifier using a transistor in place of the diode. So, as far as the output voltage is concerned, it still remains the same thing. Only thing is, instead of I naught, we will now put IE naught, right. So, this is the difference between a transistor and a diode connection. Now, we are bothered about this fact that V naught is equal to, now you can see here, Vt, which is kT over Q. There is a temperature dependent factor here, and IE naught also is very severely dependent upon temperature. It doubles for every 10 degree rise in temperature. We have said this is a leakage current of a diode, reverse saturation current it is called. This doubles for every 10 degree rise in temperature. So, this is no use as an amplifier if I do not compensate for this variation as well as this variation. So, if I want to use this as a compounder, okay, or use it as a log amplifier, I have to compensate for temperature variation here as well as here. Now, this temperature variation is a well known thing. Why? Its temperature coefficient of Vt is k over q, it is constant. So, I can design a circuit using resistive network such as to exactly get the same temperature coefficient for that resistive network, but in the opposite direction. Okay. So, this particular thing can be compensated for by simply introducing an attenuator. Let us therefore discuss how this log amplifier can be designed with proper compensation for Vt and proper compensation for IE naught. So, as far as Vt is concerned, I can design an attenuator. How do I do that? What I do is I simply say, okay, this is going to be Vi this is going to be V I by R, this is the collector current and this shall be the voltage. But after this I will put an amplifier. So, this voltage V naught here is going to be this voltage, which is minus k T over Q log V I by R I naught into this gain, which is let us say R 1 and R 2. So, 1 plus R 2 by R 1 into k T over Q minus of course log V I by. So, this is the output voltage at that point. Now, by putting a thermistor in this R 1 R 2 network, I can get over the required range of variation of temperature, this linear variation can be compensated, so that this entire thing can be made temperature independent. So, this whole thing is made temperature independent. These are standard networks, the thermistor compensated networks are available. How to compensate for this kind of variation of temperature by using the. So, these designs are already available. So, this part is something that can be temperature compensated. Then how do we compensate for this? I E naught variation in temperature is not all that clearly known. So, what is done here is, why not add, this is minus something, right, add another voltage in series with this, so that this is going to have plus here itself. I will therefore add a voltage here, please remember, plus k T over Q, this is a minus k T over Q, I will put plus k T over Q log V R by I E naught into R. So, I am adding another voltage. How do I add voltage? This is nothing but voltage of a diode whose current is V R by R. Voltage, forward voltage of a diode whose current is V R by R, just like we have. Only thing is it is a constant current now. So, if I add another voltage, how do I add this voltage? This is plus minus. So, I will have to add a voltage which is going to be in this direction, right, diode potential. So, this will be plus and that will be minus. So, this is plus minus, this will be minus plus. So, that means this is negative and this is positive voltage here added. If I do that, what will happen to this voltage now? This will become, whole thing will become multiplied by 1 plus R 2 R 1, this into log V I by I E naught R minus log V R by I E naught R. This is a constant current, V R by R, we will call it as, instead of both are constant current I R. So, what happens to this now? This becomes log of log x minus log y, log x by y, and it becomes independent of I E right, into R. So, this whole thing becomes logarithm of V I by I R R. I E naught gets cancelled. This is the way to compensate for the effect of I E naught using matched transistors. In this case, that means this particular transistor again has to be connected as a diode here. So, it will be something like this, let us say is connected as a diode, and I have to pump in current into this, so as to forward bias this by a current source which is going to be carrying a current of I R. So, you can see that this is the way I will compensate for I E naught. That means, the whole thing now is going to boil down to a nice logarithmic amplifier, where it is going to be independent of temperature variation. This has already been compensated for temperature, this gets now compensated. So, this is what is called a temperature compensated log amplifier. The circuit is this full circuit. Okay. Now that we have understood how to design a log amplifier, we have not yet gone for multiplier design, we will discuss that later. That kind of compensation may not be needed when we design a multiplier, that is a different matter. Multiplier is a block which will use a large number of such log amplifiers, okay, and then use an anti-log amplifier. First, therefore, we will understand how to design a good log amplifier, then how to design a good anti-log amplifier, then see whether such compensation is necessary at all for multiplier, because log operation and anti-log operation, when you are doing, automatically they may get compensated. So, there is no need for providing separate compensation in a multiplier. Okay. So, we will now discuss a good anti-log amplifier design. We had discussed log amplifiers, now we will discuss anti-log amplifier. Log amplifier was data compressor or compander. Now, we will discuss data expander, right. So, after compression and processing the signal, we would like to expand in the same manner. This is one of the coding techniques, right. So, anti-log amplifier. Now, what is anti-log operation? It is enough if you now interchange the position of the diode and the resistor in the op amp setup. This is always the case. If you perform, let us say, squaring using op amp in one manner, okay, the square rooting can be done by merely interchanging the element that has been used for squaring, okay, and the resistor. So, if this is V I, the diode voltage has been forced to be equal to V I, because this is ground, this is virtual ground. Okay. So, now you are forcing V I to be the diode voltage. Okay. So, diode voltage is equal to V I. That means, current in the diode is equal to V T log, okay. That is actually current in the diode is equal to I E naught exponent V diode divided by V T, which is V I by V T. So, this is the anti-log operation, right. If V I is V T log something, this will become anti-log. Okay. So, this is the anti-log operation. So, this current, when it is forced into a resistance R, will develop a voltage which is I D into R. So, V naught is equal to minus I D into R. This is plus, that is minus. So, we get this as minus R I E naught exponent V I by V T. This is the anti-log operation, or this is the data expander. Now, this also is temperature dependent. You see, I E naught is dependent upon temperature, doubles every 10 degree rise in temperature, and this is also temperature dependent because of this factor K T over Q coming into picture. So, how to compensate for that? It is very simple. If I now introduce an attenuator here and make it alpha and design that attenuator network to compensate for K T over Q, that will take care of the temperature variation of this, right. So, it is necessary that I put an alpha network for this particular thing, right. That is you put an attenuator here, okay, and I E naught has to be compensated for in a similar fashion, okay, by developing a voltage and then subtracting that voltage. Instead of just carrying out this voltage here to this point, okay, we have to now put a voltage which is not only this, but also of the forward voltage of another diode, which is having through it a constant current injected, just as we did in the earlier case. Okay. So, this is what has to be done. This can be done in the following fashion. This circuit shows how the voltage here is arranged in such a manner that it is going to now compensate for the IE naught variation. Let us see how it is done. This is the anti-log amplifier. Right. So, normally if this is Vi, this output would have been IE naught exponent Vi by Vd into Vi by Vt into R with a negative sign. So, it would have been so we will call this Vi prime now. So, this is output V naught here is nothing but minus IE naught R exponent Vi prime by Vt. This is the anti-log portion. This IE naught we want to remove and replace it with a constant, let us say IR. So, this has to be replaced by IR. So, how do we replace this? Obviously, in order to replace it by IR, I have to multiply it by IR, okay, into, let us say, this factor should be coming with I, in fact, IR by IE naught into IE naught. Okay. IR, if it is to be replaced with, I have to multiply it by IR by IE naught into IE naught. So, I have to extract a factor like IR into IE naught from something else, okay, because IE naught to be replaced by IR. So, how do I get IR by IE naught? That is possible if I have a factor like this coming from the exponent log, okay, IR by IE, because exponent of log of IR by IE naught is IR by IE naught itself. So, this factor can be obtained, that means this into IE naught if you get, okay, this is what it is going to be. It will be IR by IE naught into IE naught, which will be actually giving IR. Now, this thing can be done by multiplying by Vt and dividing by Vt here. Actually, Vt log IR by IE naught is the voltage drop across a diode which is biased by a current, constant current of IR. That means, if I bias a diode with a constant current of IR, this voltage can be developed, which will give me a factor IR by IE naught. That means, actually speaking, if I want now this to be simply coming as Vi, I have to have this Vi plus this voltage coming at the input of this Vi prime. So, if it is normal Vi plus this voltage corresponding to this V diode, then we know that this factor is going to be exponent Vi by Vt into exponent Vd by Vt, and Vd is Vt log IR by IE naught, and that Vt by Vt gets cancelled, and therefore, so we have to have the voltage this here as Vt log IR. So, this Vt cancels with this Vt, and this factor IR by IE naught here comes, and this whole thing will be IR into R exponent Vi by Vt. So, that is what we are doing here. Vi prime should be equal to, this is Vi prime should be Vi plus the voltage across a diode whose current is IR, and this arrangement gives you that. Vi is applied here and an attenuator is put. So, alpha is really R1 by R1 plus R2. that is the voltage that is generated here, alpha Vi. If there is a feedback, this voltage has to be same as this voltage. So, this becomes alpha Vi, and now I have a current here IR flowing through this diode, forced through this diode IR. So, this is IR. That means the voltage here V diode, okay, is going to be Vt log IR by IE naught. Therefore, this voltage Vi prime is going to be alpha Vi plus V diode. So, this is going to be alpha Vi plus V diode. Okay. So, we have here an alpha also coming into picture. That is to take care of, okay, Vt variation with respect to temperature. So, Vt by alpha becomes independent of temperature over the range you desire. Just as in the other case, we can have Vt by alpha becoming independent temperature by selecting a thermistor resistance here in the R1 R2 network. So, that over the range of temperature desired, the thermistor in combination with Vt will give 0 variation in temperature. That is an approximation only. So, that kind of arrangement gives you an expander, data expander, which is temperature compensated. So, let us now again find out what V naught is. V naught is going to be IE naught exponent of this voltage alpha Vi plus Vt log IR by IE naught by Vt. So, this is IE naught exponent alpha Vi by Vt plus into exponent Vt by Vt gets cancelled log IR by IE naught, which is equal to IR by IE naught into IE naught exponent alpha Vi by Vt, which is equal to IR exponent alpha Vi by Vt. So, this is a data expander with temperature compensation, okay, and this is what should be used as a decoder ultimately. Once you code it in log form and then do the processing, and then you can do the decoding, okay, so that whatever is occurring in the log form comes out of log form, gets expanded and comes in the normal form. So, this is what is normally done in the so called anti-log amplifier. Now, this is not necessary when we want to adopt both log and anti-log together to form what is called a multiplier. You will see this automatically, because let us take log of Vi. Obviously, because of current dependence, it will be Vt log, okay, IE naught, okay, by some R, let us say Vx by Rx. Okay. This is the normal log amplifier without any compensation. To this we add Vt log, okay, Vy by IE naught by Ry. Okay. Then from this we will subtract Vt log, okay, Vr divided by IE naught Rr. So, now you see what happens. This whole expression is a log conversion where Vt log, actually speaking it is log, natural log. So, we have been maintaining it as log or ln. Okay. So, we will put it as ln everywhere. Okay. So, Vt log Vx Vy divided by IE naught squared Rx Ry, this is multiplied and this is divided. So, Vr, you can see that there is a cancellation of one IE naught taking place automatically. So, then other IE naught is essential because right. When we take the anti-log, let us take the anti-log now. Anti-log will give you I E naught, okay, if this becomes the forward voltage, exponent of this voltage, which is V t log V x V y by I E naught, okay, R x R y, okay, to V r divided by nothing. Okay. So, this if it is rewritten now, this divided by V t. So, this gets cancelled, exponent log, again this is nothing but I E naught, right, V x V y divided by I E naught R x R y into V r. So, again I E naught get cancelled. So, you will see that the this is the current I. So, this current I into R is the voltage output, okay, and therefore, that into R. Yeah. Yeah. I think in this whole expression we have to have R. Thank you. R. So, this will be R into R. Okay. So, you get therefore an output voltage which is independent of effect of I E naught as well as V t. So, when we design a multiplier, we can simply take log amplifiers, okay, add the voltages, diode voltages, and subtract this reference log, and then take the anti-log, okay, of this effective diode voltage, right. That becomes the effective diode voltage, and then it is to be multiplied by R if we take the anti-log, and output voltage will be totally independent of the effect of V t and I E naught. So, when we design a multiplier, we do not have to do any compensation, it is automatically getting compensated, because you are taking log and taking anti-log.